Mr. Keith DeNivo is going to talk to you about resolution and depth of cure study for stereolithography 3D printing resins. Keith?
Thank you very much for the introduction. Today we'll be talking about the resolution and depth of cure for stereolithography. I'm going to skip over the stereolithography and 3D printing background because I know that it's been late in the afternoon and you've probably seen enough background on this. But I want to thank you for coming to my session. Okay, so let me start off with the material. What?
Very good. I like it already.
Okay. All right. So let me start off with the materials I used for stereolithography. I used 3 resins that are available from Formlabs. They are called clear, elastic, and flexible. They're all methacrylate-based monomers. And to characterize them, we used the FTIR. We also got their molecular weights from GPC. And we also printed out each sample and we looked at their glass transition temperatures via the DMA. And the clear had sort of the highest TG and elastic as the lowest TG, which we will see later how that impacts our system. Okay, so to test the lateral resolution of each of these resins, I designed a CAD file that had several lines along the surface. The lines are decreasing in width as you go from left to right. We did this because we wanted to see what was the minimum width that these resins could provide in our stereolithography system. And also we can get information about how on or how off each of the widths printed are. So we measured this by the scanning electron microscope and the optical microscope. So these are kind of what the SEM of each of the individual resins look like. For the clear, it had the best resolution since it could print out the smallest width. The smallest width it could print was around 200. The elastic was a little worse, and its minimum resolution was about 260. And flexible was the worst. It had a minimum resolution about 450 microns. And this could be due to the fact that the flexible is much more turbid than the other 2 clear resins. Okay, so what really also helps determine the resolution is the resin chemistry. The resin chemistry will determine how smooth or how sharp the sides are when 3D printing. Also, the laser spot size also contributes to what sort of the minimum width you are able to print. And this is just a summary of what I stated before, with clear having the smallest width that it can print and flexible having the highest. Okay, so next we wanted to study the sort of the kinetics, or the amount of conversion that each of these resins undergo. So a methacrylate-based system has a carbon-carbon double bond that during polymerization will break and form single bonds. So in order to observe the reaction kinetics, we took our resin sample and we placed it above a real-time FTIR, and we subjected it to the UV radiation that causes polymerization. And then we studied on the decrease in the double bond as it's polymerizing, the double bond peak, and it forms single bonds. And from this information, we can kind of get how many double bonds were converted into single bonds over time. So if we look at how many double bonds were converted, or the percent conversion, for the clear, during its polymerization, the number of double bonds were only converted to about 55% into single bonds. The elastic had the highest amount of conversion. It was almost fully converted. And the flexible had a high conversion, about 85%, but it did have a great depth dependence in terms of how thick the sample is, how much conversion would you get depending on its thickness. From this information, we can determine what the network structures should look like in each of these resins. So if we look at the network structures of each of these resins, for the clear, we don't have as much conversion, therefore its network structure should not be as tightly bound. You will still have remaining methacrylates that have not reacted yet. Whereas in the elastic, the network structure is mostly filled and you only have a few methacrylates left for conversion, and flexible would be somewhere in between. So to sort of confirm this, we subjected each printed sample to more UV irradiation. If you subject more to more UV radiation, you will get a change in its network structure. So looking at the DMA, previously the network structure was more loose, therefore you had lower TGs determined by the DMA. And after subjecting it to more UV radiation, the glass transition temperature shifts to a higher one. And the same thing occurs for the elastic and the flexible. However, in the elastic and flexible, there's a much less change in its TG as compared to the clear. So to put it visually, the clear has had a less bounded network structure, and then after post-curing, it had a more tightly bound network structure. The elastic also gained a few more single bonds, and the flexible also gained some single bonds somewhere in between the clear and elastic. And we're going to look at how that also affects its mechanical properties. So since the clear had more room, so to speak, or more double bonds to react, after post-curing it, you see a dramatic shift in its stress-strain curve. Its elongation at break is decreased, its ultimate tensile stress is increased, and you get a very dramatic change. Versus the elastic, there was not much of a change from post-curing and from its printed sample. And for the flexible, you do see a change somewhere in between the clear and elastic, which makes sense because there was more double bonds than elastic to be converted into the polymer network. So in conclusion, we showed how 3 different resins are have very different network structures, and how post-curing can increase the cross-linking within these network structures, and this affects its mechanical properties and thermal properties. So ultimately what we wanted to show was how the FTIR can give us information about these network structures And then from there, we can actually predict how much up conversion would actually change the mechanical properties. We also looked at the resolution of these three resins, and is determined by several factors, but resin chemistry is a big factor in this. So I just want to say thank you very much for listening, and I will take any questions if you have them.